Good morning. Well, good evening, really. It's 11 p.m. over here. We are in the MetaC Compiler. Everything is compiling. Everything certainly seems to work. I believe we can go and do some stuff with the expression parsing thing. But first, what we want to be able to do is to get a location on our tokens. So I've already made it such that you are able to say to store the location of a token in a 32-bit pointer, which is already inside the token, which then references the lexer state and the lexer to keep all of that stuff around. So I think once we match a token, what we can do is we have this token position, and the position is already inside the token. But the issue is that that position is a relative position. It is relative to the start, to where this token starts. So what we actually have to have for the token position to be valid is to have it be the state's position. And so that means what we're going to do is we are now going to increase the state's position by the white space we have eaten. So we say state position plus equals the amount of white space we've eaten. Then we reset the amount of stuff we have eaten, and we set the token position to the state position. What we then do is we put we say token.location ID equals lexer, MetaC lexer, really this is the MetaC location storage, start location. We pass the self location storage in there, and then we do it like that. Location storage in there, and we give it the state line. Oh, state because it's a parameter. State line, state column. Right. And once we are done parsing, at the point where we add the new position, we say token is MetaC location, storage and location, token.location ID, state line, state column, and that is that. So find this. So first we do a start on that, and then we do an end on that. Of course, we have to put the location storage as a parameter here as well. So we say lexer, which is self location storage pointed to. I believe we could copy the thing by value because it's not that big. It only contains the state to know how much is in the location array, or in C++ terms, the location vector. And all we got to do now is to implement these functions. Let's put them conveniently above the lecture here that uses them. So we have a thing which returns MetaC, returns the uint32. I may want to change that to a location pointer type. It takes a location, a MetaC location storage T, which is the location storage. It takes a location ID, which is a uint32, and I kind of don't want it to be that way. I would like to give it a proper type, but for now it's gonna be u32. You know what, let's do type def MetaC location pointer uint32, just so it's not that hard to change later. MetaC location pointer. There we go. And then So we have this, then we have the line and the column, which should be to U32 properties, line, and column, which is also U and 32T. And that is the signature for our function. We have the end location, which we just wrote. We want to have a start location as well. Just going to look almost the same. Oh, by the way, this is this is void because it takes a location pointer, whereas this one returns a location pointer. Location MetaC location pointer start location takes the location storage first, then a line and a column. As that, the implementation is also not hard. It takes location storage, location size, location storage, location storage, locations, it does location, first of all, the U and 32, U and 32 T, result equals the value of location storage, location size plus plus. Then we say that location of results should equal line. Is it start line? This should be capitalized. By the way, while it's not used very often, so it's not that hard to change. Start line equals line, the same thing goes for the start column, which equals the column. I think the start column is a 16-bit thingy. I'm a bit confused because I should just have to find a way to do meta location storage start lock. Now unlock with a capitalized thing, and we have a start lock. MetaC location storage start lock. So that works. Of course, the location storage doesn't yet return a proper location. And as always, when I deal with indices, sort of location pointers, I return result plus 4, because I want the zeros to be the indicators for invalid results, and we want to assert that location size is less than location storage location capacity, like that. And that should now enable us to grab a location pointer, and now we want to be able to set the end location. So we first assert that location ID minus 4 is smaller than or equal to location storage location size, because if it's not, then we aren't doing the proper thing. Well, heard a couple of parents around it, never heard anybody, and it makes the code easier to read and everything nicer. Alright, now we want to make sure that we get a... By the way, we can assert that we have a location ID. Assert that location ID greater than or equal to 4, which it has to be. And then we go and we do we grab the location from the location storage. So assign un32 uint 32 idx equals location id minus 4. Then we grab the location from the index. And now we do location dot line span equals location line span equals location line start line equals the line we're on minus the start line. And we could assert that line is smaller line minus location start line is smaller than OX FFF, because that's the maximum line span that we can store for now. And we say location end column equals the column we're at, and we assert that the column is smaller than OXFL. There we go. This updates the location. Maybe I should make this a UN 16T everywhere, just to note that it is actually just 16-bit. Yes, I meant that. So this compiles, which is very good. I think I want to save all the files and then quit this workspace for a second. Where is the close workspace? Recent workspaces, metal. MetaC used to be called metal. Go to declaration. I don't see why it cannot highlight the UN32, but who am I to judge that? So we do still compile, right? Yeah, we have a REPL. Help. Okay. In theory, oh, and we forgot one more thing, which has to be saved in the location as well. And that's the source index. Source ID, that thing. A token doesn't get that by default, does it? Does it? Because it might. Token gets location ID, token gets position, which is the state position. And this now also requires us to track the column. Luckily, we can do that quite easily, because the column is actually known here for the character literal, for example. What we can do is say state.column plus equals eaten cars. And we can do that because we know that there cannot possibly be a new line in the character literal. With a string literal, that's a bit different. Where we can have an escape new line inside the string literal, in which case the state column goes to 0. And at this point where we have determined the because the line can change inside a string literal if we escape the new lines, we have to count the columns. I don't love that, but I also don't see how else to get that. So let's do it. uint32 uint32t column. Because the then well, you know what, we can just set this column to 0. The state column we actually want to update because we need it for error messages. So that one should be proper. But what I can do, I can say before I issue an error message, I can update the state column so there is that. C++, that's fine the way it is. When we eat a character, we also increase the column. So if we increase the column at the back end of this, if we increase the column at the back end of this, Actually, it doesn't matter whether we increase it at the back end of this or not. We can put the column to 0 because before it will ever get registered with them, it will be increased here. So that's fine. So now that means the state tracking works properly through string literals. Here we know the line stays the same. So we can say all we have to do is to increase the column state column plus equals comment length. Plus 1. Here we have a comment that counts new lines properly. So when it finds a new line, what we have to do is set the state column to 0. And increase it we set the state column to 0. If we don't have a slash pointer, we assert because that can't happen. The offset is the slash pointer minus the text. And the column which we span to is okay. We do update the column. That's great. We already update the column. Don't need to do it in here. Nothing. Okay. So that's great. Column and line location should now be properly tracked. In order to make sure that that is actually correct. This is this. Okay. Let's go into token mode and make sure that we actually lex a comment properly. It's a comment that has the length of 10. 1, 2, 3, 4, 5, 6, 7, 8, and the 2 slashes are 10. That's fine. What I also want now is to have a line counter for each line I type into this thingy. Oh. See that as a character literal? And it gets the length wrong. So a valid character literal would be this, for example, which is too long. The literal itself is too long. Then we would have a OFF. That's also a valid character literal. But here we do get the length wrong. It's good that I'm seeing that now, because that mustn't be the case. So we update the car literal length, but we don't seem to put it inside the car literal. With a string literal we do set the pointer. With a car literal we don't do that, which we have to do. So we have to say token dot car literal length equals car literal length, and I think we do it like this. Okay, we have now a character literal, and it doesn't check them very thoroughly. So now the car literal length is 3, which is still wrong. Because we have to take a snapshot here. Q. Let's try it again. We have a character literal C. The length is 4. That's wrong. We have a character literal OXFF. The length is now 7. Item characters are 6. So alright, we have to take the snapshot before Right, so let me get that straight. We increase the column by what we have eaten. The car literal length is eaten cars plus plus minus 2, and this would give us only what's inside the thing. So if we have this should be a car literal length of 1, but it's not. I would like to know why that is. Car literal length 2, 3, 4. Okay, let's say we take the car literals with the thing. So we want to make sure that the character literal length first, let's see if we expect this to include this, because we would check that token length. When we hit a car literal, we check the car literal length and we add 2 to it. Okay. So we are expected to return the length without the without the 2 single quotes. That is alright. We just have to know that that is the case. We will not find it in the H file, but we will find it in the C file. So we start with a 1, because we reckon that a character literal would be at least 1. However, since we add the number of characters we have eaten, we should actually start with a 0, because we will eat at least 1 character. We'll eat 1 character for... Alright, so we think that the starting quote we have already eaten. So if our character literal just has one character, then we do that. Alright, let me quickly compute the longest character literal that we can have. For white characters, it would be 8. Like if we put 1, 2, like we have O, U, F, 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 which we could have. Then we would need to have that much storage inside the literal to store it. The question is, do we have that space? Let's see how big our tokens and stuff right now are. So we got to def MetaC tcc I dot run utils print sizes dxl equals xl table. Okay. So the Lexer has 8K. That's a lot. And the token has 32 byte. Why does it have that much? So 4 byte, 8 byte. The key is 4 bytes. So we're at 12 byte. 12 bytes plus 4 bytes is 16. Not 16, because we can have a pointer in there, in which case we'd have 8 byte. We have a character literal length and a character with the character variable, but that would not be enough to store a character. I think the longest valid character literal we can have would have 8 bytes. So what we can do is simply store cars 8 and simply copy each character, including the escape sequence when it comes. And that way we would still have the storage in line. We would have this as a value, and I don't think that this would increase our size of the token at all. It doesn't. It does compile, which means we never write the car variable, which is weird. All right. What we now want to keep is the length starting with a 0, because the next character we hit it's gonna end up in token.cars car literal length plus plus equals C. And the same thing happens here. If we hit an escape sequence, we store that one in the character literal as well. We increase the eaten cars. We increase the text. We do not assign car literal length because it is what it is. It does not eat the bits here, it only eats what's inside the car literal. Honestly, that looks good, if I do say so myself. Of course, this will only work if the car literal length is not smaller than it's not bigger than the size of the thingy. We can simply assert that our literal length should be less than size of token dot cars. So now we have a character literal A, and we get a character literal of length 2, and that is because we add 2. However, it does seem like we are not getting what we should be getting. So let me print the character literal at the end of the REPL. I was going to parse expressions, but having the car literals be broken, well, that's a whole different thing. Alright, there we go. Yeah, the token length gets it from that. Alright, we say else if token type equals token call literal, and we do printf of %s dot star s m, and we call this one token dot call literal length, which is the length of the string that we're going to print, and then we take token dot cars as the start of the string. Which I think should work. So we go into the took mode, say A, and it does give us a character literal with an A. Inside we can say a character literal with an alarm character inside. That also works. We have one with OXFF inside. We see that one coming back as well. However, it seems to add an empty character literal for some reason. which would imply that we get something wrong while lexing. Let's see if we can lex this properly. So this works. With the strings, everything works. With the character literals, we have issues. So here it does complain about the empty character literal, as it should. And it is at column 35 that it complains. If I do another valid character literal and I do another one that's here, that ended, we are at column 39. So the state that tracks on which line we're on, it doesn't track the line, but it does track the column. So I can quickly make the REPL track the line as well. Which would happen in the case where we hit this. This means somebody just entered a line, right? And that means the state that we use for our errors, which I think is the G line lexer, G line parser has lexer state in it, and I think that's the one that's being used. So we should be able to just have a quick look at what type the lexer state is. Lexer state is a pointer, so we go here, we say line plus plus, and then we go and then we should now get something that tracks the line. So if I put a string here, I could create a segfault in case the lexer state isn't initialized. Oh, it does use the REPL state, okay. Even for error messages. Well, it uses the REPL state to lex the next token, so I guess that is true. Well, that's better than I thought. Then I go REPL state, and I go line plus plus. In the case where we hit the end of the inserted line, which would be here. We have a little block that does REPL state line plus plus. Also REPL state column equals 1. So now if we put a string here, we have a string, and if we then trigger an error message, for example with an empty character literal, now we get it at line 1, column 1. If I say space, 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 empty character literal, we should be at column 4, line 2. Column 4, line 2. This is awesome. I'm really happy with this. Having location tracking on the REPL is really good. So now I can do fx, right, like that, and I can go expression 12 plus 12, and well, the other thing about this is we have to clean the location state. The locations up, because we just used all our locations. But what we can do for that is we can simply clean the state inside of the REPL, because we don't need to keep tokens around, right? Once the REPL sent them, they're gone. So what we can also do is say, after we process the whole line, we can do G, I think this time it is the G line lexer. We say token size equals 0. We just kill all the tokens we just got. We kill the tokens we got, and we also kill the locations. And now we should be able to use it indefinitely. Oh, could it be that I don't even use the G-line lexer? I do not think that I use the actual lexer, but maybe I do. Would be great if that were the case, actually. So now we should be deleting the location nodes of tokens that we aren't tracking. So this is string, and string literal is because we use this, right? We eat more characters, but we can now do that as long as we want, and because we are deleting the location and such, we can now trigger a error. We get the correct line number and the correct column. So we say, for example, I can trigger an error right here, which would increase the column. The line number also increases by 1. I really like this. Really like how well this REPL behaves. Colon E, 12 plus 12. Does it work? unfortunately, it doesn't. Well, when we use the parse expression call, now we do use the line lexer. Right. Not the line lexer, but the line parser. I think the line lexer as well. Now that I think about it, let me look at the line parser. I think it is. I have to find where it is defined actually. It should be somewhere. If I go into the REPL and say G line parser X and that, I should be able to go to the declaration on that. That's a thingy. The line parser uses the line lexer, and that lexer therefore has an empty location storage. Now we can change that. We can give it a location storage, which would be 0, size of inline tokens, and 0 is the size. This would be size of inline locations divided by inline locations. That's my underscore for every static variable, and this won't be great, but until I have location T, location, let's say 256. Okay. At least the parser will be able to run for a little bit. E12+12, or maybe not. So let's see why it fails on that one, because I thought that I did give it a location storage. There is a location storage in the line lexer. The location size is set, the location capacity is set, and I think I defined my line storage differently than I usually do. My location storage. No, the location storage starts with the pointer, then takes the size, then takes the capacity. But I must have initialized it wrong, since that is not what seems to be happening. So where is my G-line lexer? I think that should be in the parser, in the C file for the parser. Yeah. happens in line lecture init. And this would be 0. So first we have the inline locations. Then a 0 for the size, and then the size of the inline locations. That would be the static initialization of the G-line lecture that would work with locations. So now if we try to parse an expression, we can now, and each token in that expression knows the location on the command line. And this will come in handy once we go and write out once we do the expression parsing. Okay, I think I'm done for today, and I wish you a great day, a great night, whatever happens to be the case for you.